Now we want to look at some harder simple harmonic motion questions. And the first one here is we've got a pendulum and it beats seconds. So each half oscillation is saying we're taking 1 second. At a place where gravity is 9.812 meters per second squared. And then we move it to a place where gravity is greater because it's 9.921 meters per second. And then if that's the case, how much will it gain or lose in a day? We can take our period to be 2 pi times the square root of L on G, where L is the length of the pendulum. So we're going to have two different places here, and we put that in there and reflect it with our gravity. So if we can work out what the length of the pendulum is, we can start to work out our difference in our periods there, and then we can work out our times. So we know t over 2 is equal to 1. Because the pendulum beats exact seconds each half arc, it takes 1 second there. So it means that for the period there must be 2 to go back and forth. So 1 second and back again to the next one. So we can set that up for the first one here. If it's beating it at that point, and said 2 is equal to 2 pi square root of L on 9.812. Solve for L, so the 2's cancel, pi goes across, and we get 1 on pi, square it, and then multiply by the 9.812. So L works out to be 0.994 meters. So we do that with T bar here, which is our new place. Then that's got to be less than T because that is greater than, the gravity is greater. So it's got to have to be less than that. So the new place will start to gain because it's obviously heavier. And, well, not necessarily heavier, it has much more acceleration there. So it's going to beat faster. So that can be worked out by the difference in the times and periods over the original period, or we could write it as 1 minus the new period on the old period there. So when we go to see how much it gains, we can do that with our periods there. We get the 24 times 3600, okay, because every day it's going to do that amount. It does that many beats an hour for 24 hours. And the 1 minus the T bar on T gives us the square root of the 9.812 on 9.921, which means it's going to gain 476 seconds every day. In our next problem, we're treating tides here as they are in simple harmonic motion. So it's a bit of an artificial situation because tides don't really go in a true simple harmonic motion. It looks close to it, but they don't follow that nice pattern all the time. So, but we're using that as an idea. So, what are we looking at? We've got depth of the water when it's at low tide, okay, is 7.2. At high tide, it's 13.6. So we've got a low water at 205, so we start to set those up, and high water at 820. And if the captain of a ship needs to come in, he needs 12.3 meters of water to leave the harbour. So what's the earliest? We're looking at what's the earliest time he can leave on a particular day. So if it's 2:05 there, we really want to see, well, what's the time it gets to that point. So if it's moving in simple harmonic motion, we have a centre of motion, which we'll let Bx is equal to 0. We'll let our low water be minus 3.2, and then 3.2 there, because we're setting up a difference between 13.6 and 7.2, so our amplitude then would be 3.2. What we want to do is start to set up an equation to start to work there to see, well, what's the time when x is going to be at 1.9, because that's where 12.3 is going to be the point where we can get when the captain can take his ship out. We established that our period would be 2 lots of 375, two lots of 375, which is 750 minutes. So to do one complete revolution, take 750 minutes. So that's going to help us because if it's in simple harmonic motion, we can work out that n is equal to 2 pi on t, which leaves us value of n being pi on 375. We want to solve this equation. Now we take cos here. We could have taken sine, but we take cos here because really we're looking at 205 being our starting point. If we graphed it up, that's not at the center of motion. If we started from the center of motion, then we take sine, but it's easier to take cos in this case. Because we know our equation is going to be 3.2 cos nt plus alpha or sine nt plus alpha. You could still take sine. That's not a problem. That's quite fine to take, but it's easier in this case to take cos. We know, as we just said, t is equal to 0, x is equal to minus 3.2, which allows us to get cos of alpha being equal to minus 1, or alpha is equal to pi. So we can write it as minus, because cos nt plus pi would give us a minus cos of nt. And that's why we take cos, so we don't have to deal with an angle at the end there. So we have that as our equation now. We know what n's pi on 375, so it leaves us to go, well, x is equal to 1.9 and start to solve that equation and find what the value of t is. So we take the inverse cos of minus 1.9 on 3.2, or we could write that as pi minus cos, inverse cos of 19 on 3.2. There's cos of a negative there. And we know t would be, we can put in our pi on 375 and then multiply by 375 on pi, and then solve for t. We get t then being 264 minutes, which translates to 4 hours and 24 minutes. Which means then if we add that 4 hours 24 minutes to 205, it gives us 6:29 p.m. and that's the earliest he can leave. That's when it reaches the 12.3. To get how long he's got to leave, we can just take the 264 because this indicates our 264 minutes there. That would be 264 minutes there, which we take away from the end of the time as well, the 750, gives us the 486, which is 8 hours and 6 minutes after 205, which means that he's got until 10:11. But he did want to leave at the earliest, I suppose, but he's got between those two times before he can leave. And do the same thing on this next one. This time we've got the low water at 7:30 a.m. at 0.5, high water there at 1 a.m. and the place there is in danger of flooding when it's above 1.25. So there's our critical point there, 1.25. We take our center of motion as the point where x is equal to 0, point is equal to 0, but it's in actual fact at 1. So our amplitude is 0.5 because there's 1 between the two of them, so half of that is 0.5. And our period then, if we're going from 7:30 a.m. to 1 a.m., well, that's going to be two lots of, to 1 a.m. and then back again would be 780 minutes. So half of that time is between 7:30 a.m. and 1 a.m. We want to find out where they have danger of flooding. So basically, when you're between those two times, those two places, and what times they are. So obviously, if it's starting at 1 a.m., that's our earliest time. This is our starting point, and then we go to 7:30 a.m. and back again on that particular day. So by the time we get to 1 a.m., it's already in danger of flooding because it should be already in this range, and we'll see that in a minute. But so 12 a.m. it's already started, already in danger of flooding. So our motion simple harmonic, so we take n as 2 pi on t, and t was periods to 390. So we get pi on 390 for a value of n. We know our amplitude is 0.5, so we got cos of nt plus alpha. We can solve alpha because we know at t is equal to 0, x is 0.5. So we get 1 is equal to cos of alpha, or alpha is equal to 1. Sorry, alpha is equal to 0. So that's where we get 0.5 of cos nt there. So when x is equal to 0.25, we sub that in, and we know what n is, so we able to get cos of nt is equal to pot for half, take the inverse cos, multiply through by 1 on end, so we get 390 on pi, calculate that, gives us 130 minutes, which translates to 2 hours and 10 minutes. So then we can get our 780 minus 130, so we get 650 minutes, which is 10 hours and 50 minutes later. So what have we calculated? Well, this has been our starting point. So we've calculated our value there. So that's our 2 hours 10 minutes. So 2 hours and 10 minutes to get to that point. Then it goes down to 7:30 and back again. So that's where we're back there after 10 hours and 50 minutes. So that's what we're looking at. So as we said, we're starting at 12 a.m. So we're in trouble already when we get there. And 2 hours and 10 minutes after 1 a.m. gives us the 3 a.m. So that's where we get to that point. 1 o'clock in the morning plus the 10 hours 50 minutes means that it's back in trouble at 11:50 a.m. And then that exists because it's 13 hours complete revolution. So we go to 3:10 a.m. and it's safe again after 13 hours there, so 4:10. So there are our times that it's not safe, because there's going to be another 10 hours 50 minutes before it goes down again. So that's what we're looking at with simple harmonic motion. It's not exact, but we're using the ideas of simple harmonic to show these, what happens with some of these practical examples, and how we are able to manipulate and get our equations to solve the problem that was at hand.